Hey there, welcome back to Short Takes 331. Today, we're going to talk about matrix multiplication part 2. So we had in the previous video what I would like to call part 1 of our discussion of matrix multiplication, which also involves matrix vector multiplication. But in this one, I would like us to talk about mechanics and cost of matrix multiplication. So suppose you have a matrix A whose elements are real numbers, and this could be complex numbers or any other field, it doesn't really matter. But let's assume that they're real numbers, and this matrix is of size m by n. And let's say we have a vector v, also with real elements of size n, so n components. And let's also have another vector w belonging to the same set of real numbers and n components. And so these two vectors belonging to the same set, the same vector space, can be multiplied in this way, in the conventional way, conventional definition of a scalar product. And in fact, it doesn't have to be any conventional definition, but let's assume that it is for the sake of this discussion. And when you multiply these two, when you calculate the inner product in the conventional way, component by component, you get a number. And the number will be a real number if these two vectors are real. And the calculation goes like this. You take one of the components, you multiply by the other component of the other vector, and then the next component by the next component, and the third component by the third component, and so on, and then you add it all up together, and that gives you this constant c. That is how you perform vector inner product, vector multiplication. So you have n components multiplied by n components, all added together. And what that costs, what is required to perform that full operation, is n multiplications and additions, roughly speaking. So you have to multiply this guy by this guy, and the next one by the next one, and the third by the third one, and so on and so forth, and then add them all together. And that's what we call order n operations, where n is the size of the vector. Moving forward from here, you can consider matrix vector multiplication as a set of multiplications of vectors by vectors. Let's see how that works. So remember, in matrix vector multiplication, if this matrix is of size m by n, then and your vector is of size n, then you can take this vector, this row of the matrix, and multiply by the column. And so you have n components by n components, and then you put it in the first place. And then you take the next row and you multiply by the vector in the same way, and you put it on the second location here, second spot on this vector, and then the third one, and so on and so forth. And then you get to the mth one, the last one, you multiply it by the vector again, and you put that in the last component. And so you calculate m components in this way. And so what we're doing is we're taking these m row vectors and we multiply them by this column vector. And so we're doing m times n multiplications and additions. In other words, we can regard this matrix vector multiplication, which gives us this vector u as a result, as m operations of vector multiplication. So we take this guy by this guy and the next one and so on. And so m times we do n multiplications and additions. And so the cost of doing this is of order m times n. So that's how it scales. And that's what we mean by order n here. If you make the vector much bigger, then it's going to scale linearly with n in the case of vector multiplication. But in the case of matrix vector multiplication, the cost is going to scale quadratically with m and n. Or more precisely, if a is square, you see here how the quadratic order appears. So if as a is square, it's of size n by n, then this m and this n are equal to the same number. And so the way the number of operations scales is as order n squared. So what this means, for example, is if your matrix is of size 4 by 4, then you're going to see some cost in the matrix vector multiplication. And if your matrix grows by a factor of 2 and now becomes 8 by 8, then you're going to see that the number of operations scales up by a factor of 4. Okay, going from 4 by 4 to 8 by 8, you scale the matrix by a factor of 2, but the number of operations required to perform matrix vector multiplication scales like the factor of 2 squared, and so that scales by a factor of 4. So you see, it could be very costly if you are talking about a very large increase in the number of matrix elements. Similarly, matrix products, which can be regarded as a collection of these things as well, will scale like the order m by n by p if the matrices involved are of size m by n and n by p. And so what we mean by that is depicted here. So suppose this is one of our matrices of order m by n, as we had before, and now we have p column vectors of size n, And so this matrix is of size n by p. And so the resulting matrix is of size m by p. This is what we saw last time when we discussed matrix multiplication. And so the cost of obtaining the result is basically the m by p times performing n products and additions. So we have m by p if you want vector-vector multiplications, because you have to take each of these guys, multiply by each of these guys, and so on. And so that's going to be done m by p times, and each of those m by p times costs n multiplications and additions, and so that's why the cost scales like m by n by p. Or if you want, you can say m by p by n. If all these numbers are the same because the matrices are squared, then this scales like order n cubed. So you see once again that if the cost of calculating a matrix product of size 4 by 4 is something, then when you go to 8 by 8, it's going to scale not by 2, not by 4, but by 8. It's going to scale like 2 cubed if you double the size of your matrix. And so you see here how dealing with matrix multiplication is a very expensive type of operation, and whenever you can, you should try to optimize that or try to avoid it altogether if you can. So if you enjoy this series of videos on linear algebra, please consider liking the videos and subscribing to the channel. It would really help us. This is meant for my students at UNC Chapel Hill, but if you're not a UNC student and you're looking for a tutor in physics or math, in English or in Spanish, you can contact me. You can do so at shorttakes331@gmail.com, or you can leave a message in the comment section below and I'll get back to you. Now, these operations, as you can see, as I was saying, are very costly. And so you can ask, can we do better? Can we do better than order n squared for matrix vector multiplication, for example? So in that case, we're taking m times vector-vector n component multiplication, and so that's why it costs m times n. That's where the cost comes from. Or if you want n squared, if you're talking about m equal to n, what can we do? Well, one thing that happens sometimes, and this is rare, but it happens sometimes, is that this m times can be improved upon in special cases. And this is the case of a Fourier transform. So if the matrix in your matrix vector product represents a Fourier transformation, and we will see what Fourier transforms are in a future video, but if that's the case, then it is possible to simplify this part. And basically what happens is that every time you calculate one of the components in the result, you actually get another component for free. And taking advantage of that property, or almost for free, I should say, not exactly for free, but almost for free. And so taking advantage of that property, you can scale down from order n squared to order n log n. Okay, that the Fourier transform matrix is very special. And so in that case, you can simplify it and get a much faster performance. This is what's called a fast Fourier transform to take advantage of that. And it's one of the crown jewels, if you want, of computational or applied math in general, and one of the crown jewels of computational physics when you can use it. So we can also simplify the vector-vector part. And you can ask, well, how is that even possible? I have n components of one vector, n components of another vector, so there's no escape. That's just going to cost n if you multiply all of them together and then add them all up. How can you get away from that? And the reason you can is that in some cases, in fact, in many cases of interest, you will be dealing with sparse matrices. So in some cases, these rows that appear in your matrix that you use to multiply by a vector have a lot of zeros, or rather very few non-zeros. And this is what we call a sparse matrix. And we'll come back to that in a future lecture. But take, for example, this case where you have 1 minus 1 and then all zeros. And then the next row is 0, 1 minus 1 and a bunch of zeros. And the next one is 0, 0, minus 1 minus 1 and a bunch of zeros all the way to the end, and so on and so forth. So when you know this, when you know the structure of the matrix that has only a couple of non-zeros and everything else is 0 for each row, then the cost of the vector-vector multiplication is just 2. It doesn't scale like n. So it would scale like n if we didn't know what's going on here. If all these numbers were in principle non-zero, then there's no escape. But if we know where the non-zeros are, and we know that there's only 2 or 3 or a small number of them that doesn't scale with n, then the cost of matrix vector multiplication would scale like order 2n instead of order n squared. Okay, so that's very different from the Fourier transform case. This is taking advantage of these m times. And here we can benefit from the fact that in some cases with sparse matrices, there's only a few specific places where we have non-zeros, and the number of non-zeros is what enters in here, number of non-zeros in each row. And so you see that it's important to know different kinds of matrices and their properties. That will help us solve a lot of problems. It's useful to understand the different matrices do different things, and they can have special properties that allow us to accelerate our calculations. And we'll talk about some special matrices and some other properties in the next video and in other future videos as well. So this, as I was saying, will help us solve linear problems in physics. The linear problems, as I mentioned in a previous video, and I'd like to repeat here, are problems that can be written in this form. A linear system of equations can be written always in this form, where you have your matrix of coefficients, your unknown. This contains x1, x2, x3, and so on, as many as needed. And then you have your right-hand side, all your right-hand sides of the equation, the parts that don't depend on x at all. And in physics, what will happen when you have to set up a system like this, typically the matrix A encodes how your system responds. X is what you want to know. It's the stuff that gives you your electric field, your magnetic field, and so on. This is what you want to know. You want to know those fields, typically because you want to know the forces on something else due to those fields. And here, on the right-hand side is usually an external excitation, something that somebody else does from the outside, or the charges present in your system, and so on. And so this is what comes from outside. This is what you want to know, and this encodes all the physical response of your system, including in some cases boundary conditions. And I'll give you some examples of that. The first example that comes to mind is with the so-called Poisson equation, where you have the Laplacian of the electrostatic potential equals to essentially the charge distribution. So this is what's imposed on you by your problem, your distribution of charges, where they are in space. This encodes the response of electromagnetism. This Laplacian really it comes to you from electromagnetism, from Gauss' law, and so on. And this phi is what you want to know. You want to know that potential, because if you have the potential, you can take a derivative and you can find the electric field. And if you have the electric field, you have the forces on everything that you're interested in, on any test charge that you send through the system. And so our job then is to solve this problem, and we will be better able to solve this type of problem if we understand more about matrices. And in this case, where is the matrix? Well, this object will play the role of our matrix in this case. And similarly, in the wave equation written down here in sort of relativistic way with this square operator, this is the wave operator, then you have your unknown, the form of your wave, and this f is source, something that somebody does to excite that wave. And similarly down here, when you have the equation for the forced harmonic oscillator, you have your second derivative coming from Newton's law, you have your Newton's second law, you have your spring constant k coming from Hooke's law, and then you have something that somebody does from outside. Somebody inserts energy into the system by moving whatever it is that it's oscillating, your pendulum or whatever, at some rate given by this function f of t. And then if you solve this problem, basically you solve for x as a function of t. And in all these cases, and certainly in this one, what we're doing is we're putting this operator or this one on the other side of the equation. We want to solve for phi. That amounts to putting this guy on the other side of the equation. We solve for psi here by putting this wave operator on the other side of the equation, and the same here. X of t is obtained effectively by putting this whole thing in parentheses on the other side of the equation in some way that we will discuss. And so that then amounts to finding the inverse. And if those operators that I mentioned here, Laplacian, the wave operator, and this object here, they take the form of matrices, and in many cases we will see that they do, then our job is to find the inverse of that matrix. And this is really at the core of one of the main functions of linear algebra, to find the inverse of matrices and to establish under what conditions those matrices have inverses, and when these problems can be solved. And we will begin then to talk about that in a few lectures, in a future video. So next time what we will do is we'll talk more about special matrices and the different kinds of properties, and we'll then build the framework that will allow us to talk about how to solve these linear problems. And with that, I hope you enjoyed this video. If you did, please like and subscribe. If you need a tutor in physics or math in English or in Spanish, then if you're not a USC student, I'm happy to help you. And you can reach me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. Until next time.